Hey, North, Mr. Yergler here. This video is going to go into an introduction into thermochemistry. And thermochemistry is just the study of how energy relates to chemistry. And so we need to start by talking about energy and work and kind of identify what those things are. So energy is, by definition, the ability of a system to do work or to transfer heat. Okay, most of the time we're going to be talking about the transfer heat part, but work is a component of that. We'll spend a little bit of time on that. Just as a reminder, the total energy is always conserved, so energy is neither created nor destroyed. This is the first law of thermodynamics. So heat is always transferred, heat or work for that matter, is always transferred. It's never just like, it never disappears and it never appears. Whenever we're talking about work, as far as we're going to talk about work, it's going to be in the context of an expanding gas. Okay, so we can use an explosion or some sort of expanding gas to talk about work. We have to distinguish between the system and the surroundings. The system is always the reaction that we're looking at. That's going to be the amount of gas that we have. The surroundings is basically everything else, so everything around that. So in this context, if we're firing a huge cannon, the system is going to be the expanding gases, right? The reaction that's taking place. And then the surroundings can be a couple different things that are important. For one, the projectile, but also the barrel of the cannon, because there's a lot of heat transferred into the barrel of the cannon. And this actually represents both work and heat, because the work is represented by the projectile because it's moving and it has a displacement, and the heat transfer, it can be represented by the barrel, because the barrel of the gun is rigid, it's not moving, but it is warming up. So here's our formula. Energy is work and heat combined, right? So we just add them together. We can think, this is a more generic way of thinking about it. Heat and work can both flow from the surroundings to the system or from the system to the surroundings. So we can talk about the system doing work on the surroundings, or we can talk about the surroundings doing work on the system. Let's talk about work for starters. Work, it can be done on a system, what I just said. In this case, it'll be positive, and this would be compression of gases. It can also be done by the system. If the system is doing work on the surroundings, then it's going to be expanding. We're only going to be talking about gases when we're talking about work. You could talk about work in a lot of other scenarios, but we're only going to be talking about gases, and so we're only going to be dealing with pressure and actually volume as well. And here's the formula actually for work. Work is the constant pressure, so pressure is always going to be constant for our situations, and there's a change in volume, so an expanding gas or a compressing gas. Again, let's think about this cannon. The system is going to be the charge in here, the powder charge. The change, because there's a change in volume when this is ignited, the gas expands and increases in volume, and so it does work on the shot, and the shot will obviously go flying out of the cannon. Okay, if we think about it more from a molecular standpoint, these molecules are constantly colliding with the surfaces of their container. They have two options. They can only transfer that energy as heat, meaning that the molecules of the container start getting warmer, or they could transfer their energy via displacement. They could change the displacement of the piston, right? And so the piston could move to the left, and that would only be done by the energy of these molecules colliding with that surface and moving it across, okay? So this energy reaction really makes sense. There's only two ways that these molecules can transfer energy. They can either heat up the surroundings, or they can increase the volume and create a change in displacement on the surroundings. Now, to calculate the delta means change, and so it's always going to be final minus initial. Never get lazy and do initial minus final. You'll screw up your signs. Always do final minus initial. This is a picture of dry ice, so solid carbon dioxide. As it sublimes, as it goes from solid to gas, we're expanding the volume, right? So our final volume is larger than our initial volume, and so we can say that the system did work on the surroundings because of the expansion. I like to think of it too as work is leaving the system, right? Because work is being done on the surroundings. And so because of this, we have a positive delta V. And if we plug that into our formula, we're going to actually get a negative W. And this is consistent with the idea of work leaving the system. Just like heat leaving the system is negative, work leaving the system is also negative. If we compress the gas, then the initial would be larger. We'd have a negative delta V and therefore a positive W. All right, let's talk about heat. So there's two options, endothermic and exothermic, and we've talked about this a lot before. You're already familiar with these terms. Energy going into the system versus energy going out of the system. And again, the same thing can be thought of as work. Work can go into the system and work can go out of the system. the signs are the same. Negative is always leaving. Make sure you're familiar with these. The surroundings will get cooler with endothermic because it's absorbing energy from your hand when you touch it. And in exothermic, it gets warmer because heat is being transferred to the surroundings. So a couple examples. Water going from solid to liquid would be endothermic. It has to absorb energy in order to melt. And then the opposite would be obviously exothermic. To go from liquid to solid, this is a little less intuitive. When you put ice trays of water in the freezer, that's actually an exothermic process that's going on. This is a little bit less intuitive, but as you put water into the freezer and it freezes, it's losing energy to the surroundings, which is the freezer, and you end up with obviously a solid piece of water, which is ice. So really just a couple main takeaways. Make sure you're keeping your signs straight. Negative is always leaving, positive is always coming in for both Q and work. And work is going to be limited to expanding gases, and so we need to look at changes in volume. If you have any questions about it, be sure to write those down, bring them to class, and we can discuss them there. All right, this is Mr. Yergler signing out.